Hey everyone, so let's continue our discussion on the graph of a complex number. It will basically be drawn on a complex plane. So as you see on the slide over here, we have a complex plane. The difference between a complex plane and any other plane is that a complex plane, rather than having an x and a y axis, it has an imaginary and a real axis. The horizontal axis is the real axis and the vertical axis is the imaginary axis. What I mean by that is that all the real points, that is, if you have a complex number like 2 plus x equals to 2 plus 2i, the real part will be dealt with respect to the horizontal axis, and the imaginary part will be dealt with respect to the vertical axis, which will be the imaginary axis. So we already discussed this. I just wanted to go over this once more. Another thing that we discussed was the argument of the modulus of a complex plane, which is of course the line OP, that is from the origin till the point, which is represented by a z modulus over here. So basically what this would be the square of x square plus y square, that is the square of real part and the imaginary part and the under root of that. That way you can find the modulus of this point. This we discussed in the previous lectures. In this lecture we'll start with the argument that we use in the complex plane. So the way to find the argument is that first of all we have to look at the angle over here. So this angle over here, that is known as theta, is the angle that this line over here makes with the real axis. So this theta would be the line over here that it makes with the real axis. Now how do we find this angle over here? So I'm sure you remember sine, cos, and tan. We can use that to find this angle over here, because if you see over here, we can make an imaginary triangle. This value will be equal to the imaginary value, that is y, because you know this is y points away from the horizontal axis, and this will be x. So how do we find that? Can we use sine, cos, and tan? Yes, we can. We can use tan over here, because tan is basically perpendicular, that is the side opposite to the angle, over the base, that is the side adjacent. So you see, this would make the hypotenuse of the triangle, this would be the perpendicular, and this would be the base. So we can basically use this formula over here. Tan theta would be y over x. In order to find the argument, we basically take the inverse of tan, and then through that we can find the argument of this graph over here. This graph that we also called the Argand diagram. And so this is pretty straightforward, because you know there's no complexity in this. Just remember that you have to find the modulus and the argument. There's straightforward two ways to find that. So all of that is summed up in this slide over here. You can see that the modulus, this contains a modulus equation and a modulus statement, the definition and the definition of the argument as well, and the statement of the how to find the modulus and the argument of a complex number. So this is all there is to the argument, the modulus form of a complex number. Another thing I want you guys to know is that the argument has a range, and that range would be from positive pi to negative pi. Why am I saying that it's going to be from positive pi to negative pi? Because this is expressed in radians. So because it is expressed in radians, it can only take the form of pi. Now you might be confused, why isn't it from pi to 2 pi rather than from pi to negative pi? If you see, the whole range from pi to negative pi actually covers the total value of 2 pi. Otherwise it would have been from 0 to 2 pi. So that is one thing that you have to remember. Secondly, it has something to do with the direction of the angle, which I will explain to you with the help of an example. Let's take an example. We have this question over here: find the modulus and argument of 4 minus 4i, that is negative 4i is the imaginary part and 4 is the real part. So how do we go about finding this? Okay, the first thing that we have to do is we find the modulus. How do we do that? We take the real part, we take the absolutes of this, we take the real part over here and we square it. We take the imaginary part and we square it, and then we under root it. So we get basically under root of 32. Under root 32 would basically mean 4 into 4, that would be 16, multiplied by 2, that would give us 32. So we take the 4 out, so we get this answer over here. Another thing that we have to do is we have to find the argument of 4 negative 4i. Now you see, first of all, what I would like you to do is, that's not shown over here, is plot this value, so that you would know where on the Argand diagram this value would be, where on the argument diagram this point would be. Now negative 4 over 4, that would basically mean, as we can see over here, somewhere around over here. because this is how we find it. We basically, like I told you, we have to take a tan because we make an imaginary triangle. So the tan would be and tan theta would be -4/4, and we find the value of the theta by inversing the tan. By using the tan inverse, that will give us -4/4. Now solving that will give us tan inverse of -1. Now if you see over here, this is what I wanted to tell you. Look at this small graph over here, -4 and 4. What did this tell you? This tells you that the real part is 4 and the imaginary part is -4. So this would be someplace over here. The point would be over here, that is in the fourth quadrant, this being the first, second, third, and this is the fourth one. So this point would be over here. So when you inverse tan, that would give you -4/4, that you'll get tan inverse of -1, and the answer would be -pi/4. Now this is where I would explain to you why we need negative. You see, if we were to have any point in this region, that is the first quadrant and the second quadrant, then we would have a positive value of pi, because this over here represents from 0 to pi. This arc that I'm making over here, this represents 0 to pi. So we're gonna get 0 and we move on, we get pi/2 over here, and we go on and we get pi over here. Now in the negative direction, we start from here. So we get pi/4, then we get -pi/2, -pi3/2, and 3/4, and then we get a -pi over here. So it's pi over here and -pi over here, so that makes a total of 2 pi. So because we are traveling in the opposite direction than we usually go, we are traveling in the opposite direction than the convention that we have, that's why we're going to give it a value of -pi. Had it been 4 plus 4i, it had been some place over here in the first quadrant, that is 4 on the real axis and 4 on the imaginary axis. So we would have then a positive value of pi, and we would have the same value, that is tan inverse of 1, and we get pi/4. But since we're going in the opposite direction, we have a -pi/4. So every complex number can be written in terms of its modulus and argument. This you have to remember every time, because you might be asked to represent complex numbers in which there is no real value. You might be asked to find the argument and the modulus of 2i. The way to do that is the same, that is you have to find the square of the real number and the square of the imaginary number. In this case there would be no real number and you would only have the imaginary number, so 2 square would be under root of, so the answer would be 0 square plus 2 square under root whole, and you're gonna get 2, of course. So remember that every complex number, no matter how complex it is, by that I mean no matter how small and big that is, you can find the modulus and the argument of that. So that's pretty much it for the modulus and the argument. We're going to continue this discussion right now in this lecture, and we're going to talk about, take a step back basically, why do we even need complex numbers? Like, what is the role of complex numbers? Why do we even have an invention of complex numbers? Why can't we just deal with math and work out every question in math and physics and engineering with just the real numbers and imaginary numbers? So let's talk about that now. So the reason basically why we have complex numbers is because we have stuff like this in math. We have x square is equal to -1. Now how are we going to solve this? There is no way to solve this equation in real numbers. We discussed this early on in the first lecture as well. I just wanted to now connect this with the quadratic equation. There's no way to solve this equation. Even the second equation, 2x plus 5 whole square plus 7, if you go on solving this, you'll find out that there's no way to solving this question. So in order to solve the problem of under root of -1, which basically means the under root of any number, under root of -25, under root of -4, under root of -16, 17, in order to solve this issue, we have the complex numbers to help us with it. Of course, this is the remaining other under roots of negative number. Basically what it means is that for any positive real number a, that is if you have an under root of a negative number, if you have a negative number inside of a, inside of the under root, inside, if you have a negative radical, the only way to go about that is solving that is through a complex number. You're gonna remove the negative by bringing a complex number out of it, and then you're gonna get the answer to that question. Now if you go on solving these equations, now x square is equal to under root of 9. Of course you know how to solve this one. What about x square plus 25 is equal to 0? You're gonna get an equation x square is equal to under root of negative 25. And the same goes for the next equation, x squared minus 6x plus 13. Now before you go on solving this equation and trying to find out whether this will give us a complex number or whether this will give us real roots, how about you find that out through another method? We have all heard of the quadratic formula. We know what the quadratic formula is and how to solve that. An easy way to find out whether this is going to have a complex roots or unreal roots or real roots, sorry, unequal real roots or repeated real solutions, is to check for the discriminant. A discriminant is the part of a complex of the quadratic formula which is inside the under root, which is b squared minus 4ac. So you use that to find out whether this will have a complex root or not. If the answer of b squared minus 4ac is, of course, first we have to represent the equation in this form. Every quadratic equation can be represented in this form, ax squared plus bx plus c. That is, there are three values in a quadratic equation. If some is missing, we just don't count that in the quadratic equation. Over here, ax squared, a will be 1 plus bx plus c. B would be negative 6 and c would be 13. You use that to find out the answer to this b squared minus 4ac, that you use that to find out the discriminant. If the discriminant is more than 0, that means that it will have two roots and both will be unequal and both will be real, and both of these roots would prove to you that you do not need a complex number to solve this quadratic equation. On the other hand, if you have the b squared minus 4ac, the discriminant equals to 0, that will basically go on to prove that you will once again have real solutions. You don't need a complex answer to this. You have a real solution, but you will have repeated real solution. That is, you might have a plus minus. That is basically what happens if you have under root of 9. You might have a plus minus 3. Now finally we come to the problem at hand, and that is, if you have b squared minus 4ac, that is the discriminant less than 0, then you can rest assured that you don't have any real roots of this answer. The answer would have complex roots. The answer would have a complex solution. That means that answer is going to have an imaginary part in the solution. So this is an easy way to find out before you actually start solving the equation, and you keep on solving and solving, and in the end you find out, oh, I have a negative radical, I have a negative number inside the square root. So before you actually do that, you can find this out with the help of the discriminant, whether you're going to have a complex solution to the equation or not. So let's try this. Let's look at some of the equations over here, and let's try to find out the discriminant in this, and let's try to find out whether we're going to have complex roots or we're going to have real roots. So starting with the first one, 2x squared plus 3x plus 1. Now what is b over here? B is 3, a is 2, and c is 1. So b squared is going to be, go back, b squared is going to be 3 squared, that is 9, minus 4ac. 4 into 2, 8 into 1, that is also going to be 8. So 9 minus 8 is going to give us 1. So basically what that means is that b squared minus 4ac is going to give us two unequal real roots, two unequal real solutions. That is, it's going to be of the discriminant is going to be the first category. Moving on to the second one, 5x squared minus 2x plus 4. So b squared is going to be negative 2 squared, that is going to give us 4, minus 4 into 5, that is 20, multiplied by 4, that is 80. So 4 minus 80. Now this one is going to give us a complex solution. Why? Because we know that the discriminant is actually less than 0. So when we have a discriminant less than 0, we know that the answer is going to be a complex equation, complex solution. Moving on, we have 4x squared minus 4x plus 1. Now b squared over here would be 16, because minus 4 squared is equal to 16. Minus 4 into 4 into 1, that's again once again going to give us 16. So in this way we now have solution to all these three in three unique ways. For the third one, we're going to have equal real solutions. If it's 0, we're still going to have a real solution. We're going to have a double root. But if it is more than 0, we're going to have two real solutions unequal. If it is less than 0, we're going to have a complex solution. So this is the way to find out whether your quadratic equation is solvable through the method that you usually do, whether it's going to have a real solution or a complex equation and complex solution. And before you start solving any quadratic equation, find out whether it's going to have real roots
or it's going to have complex roots, so that you would know that just in case if you mess up your calculations in between, you would know whether the answer is correct or not, whether it was supposed to be an imaginary answer or just a real part. So this is pretty much it for this. Thank you very much for watching. We'll continue this topic of complex numbers in the next lecture. Thank you very much.